Good day and welcome back for part 3 of our discussion on derivatives and rates of change. In the previous two videos, we've introduced the concept of the derivative at a point and the various interpretations that we have. In the remaining videos for this section, we are going to explore several common examples that one would encounter. So, the most computational example that we would encounter is one where we are simply asked for a given function to determine f prime of a, where a is simply a value where the derivative is defined. Now note, this is a very general question. We could make it more specific by asking you to say find f prime of 4, but we're keeping it as general as possible. So recall, when you're asked to use the definition, which is our only approach at this point in time, our starting point is always going to be the limit of this difference quotient. And I just write that out. So the limit, as h approaches 0, of the quantity f of a plus h minus f of a, all divided by h. And remember, one of the difficulties getting started is this function composition. And a really good way to think about this is to just simply replace your independent variable x with another symbol. In this case, I'm going to think of x as being represented by a blank space. So whatever goes into one of these blank spaces must go in the other ones. So in this case, this is the limit as h approaches 0 of f of a plus h. So that would be 1 over a plus h plus 3 minus f of a, which is 1 over a plus 3, all divided by h. And once we get it to this point, that is, we've substituted in the function, now what remains is a limit problem. Our goal is to get it to the point where we can use our limit laws, but note, we most certainly cannot just plug in h equals 0. That would cause us to divide by 0. So we need to do some type of algebraic manipulation, and the only reasonable algebraic manipulation I see would be getting a common denominator in the numerator. So let's go ahead and do that. I'm going to multiply this second fraction by a plus h plus 3, divide it by a plus h plus 3, and we are going to multiply this first fraction by a plus 3 over a plus 3. So in either case, we're multiplying by 1 in a fancy way so that we get the desired common denominator. So let's do a little bit of quick algebra. We have the limit as h approaches 0. We still have that h in the bottom. Now in the top, we're going to have a single fraction with denominator a plus 3 times a plus h plus 3. We have an a plus 3 coming from the numerator of the first fraction, and we're subtracting away the quantity a plus h plus 3 coming from this numerator we have in the second fraction. And this gives us a whole bunch of simplifications to do. Note, the minus sign really distributes through, and we have a positive a plus 3 minus a minus 3. Also, let me note, we can go ahead and take this h, which is in the bottom, and we can move that up a level and put it into the denominator of the fraction in the top. And if there's any confusion there, think of this as something like a fraction a over b divided by c. No, when we have this, you can simply almost kind of just bring that c up a level, because multiplying or dividing by c is really multiplying by its reciprocal, 1 over c, and it gives you that a over bc. So simplifying this, as we've suggested, we have a minus h in the top. In the bottom, we have a plus 3 times a plus h plus 3, and the additional h that we have brought up. So again, we have an h and an h that cancel, and things are looking quite good. And note, we're using proper mathematical notation, writing our equal signs, our limits at each step, organizing our work in a nice single vertical column. making it as easy as possible for someone to follow and read. And now we get to the point that it does make sense to substitute in h equals 0. Because when we do, we will not be dividing by 0. And there's several ways to go about this. You could use your limit laws, but I think the easiest possible approach is to just note that the function that we are taking the limit of, this is a rational function in h, which means we can use our substitution property that we've previously discussed, and we can substitute in h equals 0. So that would give us a minus 1 over a plus 3 times a plus 0 plus 3, which is equivalently minus 1 over a plus 3 squared. So what we have found for this function f of x is that f prime of a is equal to minus 1 over a plus 3 squared. And as mentioned, this is a very general question. We have a formula for the derivative at any value a where this quantity makes sense, i.e. we wouldn't want to choose a equals minus 3. So for example, if you wanted to know, and you can pick your favorite number here, which is not 3, let's just say 0, f prime of 0 would be minus 1 over 0 plus 3 squared, which is minus 1/9. And let's move on to one more example to wrap up this video discussion. Another common example involves using the graph of a function to see if we can determine when is a derivative going to be positive, when will it be negative, when will it be equal to 0. And this will nicely lead into our next section where we talk about maybe starting with a function and graphing its derivative. So the reminder that will kind of guide us through this problem is that we have this nice geometric interpretation. F prime of a is a number, and this number tells us the slope of the tangent line at x equals a. And usually the advice I give is determining where that derivative is going to be 0 might be the easiest thing for us to see immediately upon inspection. Because the derivative will be 0 when the slope of the tangent line is 0. And what type of line will have a slope of 0? Hopefully you're thinking a horizontal line. And note it looks as though there's kind of 2 points on this graph where when we draw the tangent line, it will be horizontal. So immediately what we can note is that f prime of a is equal to 0 at precisely 2 values, when a is equal to 0 or a is equal to 2. And then the question remains, where is that derivative going to be negative? And where is that derivative going to be positive? And all we need to do is kind of look away from those values at 0 and 2. So for example, if you pick any value of a, which is to the left of 0, doesn't matter which one. And so I'm just going to randomly pick a value and think about the corresponding point on the graph. When you draw the tangent line, does that tangent line have a positive or negative slope? And hopefully you're thinking negative, right? As we move to the right, it's getting smaller. So this would be a negative slope. So f prime of a is less than 0, i.e. the slope of the tangent line is negative, when, in this case, we can say a is less than 0, and there might be more that we add to it, but we need to continue investigating. If you pick your favorite point a between 0 and 2, once again, it does not matter which point you pick, so maybe say right about here. If I draw the tangent line at that point, note the slope of the tangent line is going to be positive. So f prime of a, the value of the derivative, will be positive when a is between 0 and 2. And then similarly, if you pick your favorite value bigger than 2, look at the corresponding point on your graph, draw the tangent line, you have a clearly negative slope. So f prime of a is negative when a is less than 0 or a is greater than 2. And drawing the tangent lines and just thinking more intuitively or geometrically of what their slopes will be, positive, negative, or 0, allows you to answer the desired question. Now, just to foreshadow something we're going to see in our next section, with this information in mind, can you sketch a rough graph of what we expect f prime of x to look like? Doesn't need to be perfect, but just have kind of these key characteristics we've identified. Where should it cross the horizontal axes? Where should it be negative? Where should it be positive? So what I'd like you to do is to pause the video and take maybe 30 to 60 seconds and see if you can come up with a rough sketch of what f prime should look like. Okay, so now that you've done this, let me walk you through kind of my thought process. We know that f prime is going to be 0 at 0 and 2. And then I know that the derivative f prime is going to be positive between 0 and 2, negative to the left of 0, and negative to the right of 2. So the roughest such graph I could sketch would maybe be something that looks kind of quadratic in nature. And we could certainly go into more details thinking about where the derivative will be larger in negative versus smaller in negative, but we're going to save that for future discussions. For now, this rough sketch is what we're looking for. And in our next video, we will continue on investigating more common examples involving the derivative of a function at a point and rates of change. But don't forget, there's plenty of great suggested problems for you to work through in the book as well, so make sure you're taking the time to do so. So stay tuned and take care.